if you remember, when you talk about the idea of a rate, what you're really looking for is the relationship of one quantity to another. So that might be something as simple as miles per hour, right? That's how many miles you cover in how much time tells you how fast you're going or how quickly. But you can also use any kind of rate like miles per gallon, right? That's a similar relationship for a car, but neither one of those it's not really a speed, it's a rate. So depending on how many gallons you've spent, you have a reasonable understanding of how many miles you've spent and vice versa. But you may even have something a little less related in the sense of like an exchange rate, right? US dollars to British pounds. And all those represent rates because rates are ratios between two different quantities. But often the two quantities are related by some third quantity. So let's think about the idea of if I am on the mound as a pitcher throwing a baseball towards home plate. And what I could do is I could take the trajectory of the ball, right? Supposing I'm throwing, some sort of breaking ball and it changes in midair. And I can measure and sort of an XYZ 3D coordinate position. But really what I'm doing is I'm taking time measurements with like a radar, and that's telling me where I'm at. And so realistically, X, Y, and Z are actually all functions of time. I can map the X position over time. I can map the Y position over time, the Z position over time. And so while X and Y are going to be related because of the way the ball's moving through space, they're all underneath related to that time quantity. Now, if you have two functions and they're differentiable with respect to time, so again, thinking about the baseball, it moves smoothly through space. It doesn't discontinuously move. So it's going to be perfectly fine to be differentiable. Continuity is not enough, but just trust me that it's going to be differentiable. But so if that is true, then you can try to express something that's not related to those two explicit variables. An example of this is BMI. So if you take your mass in kilograms and your height in meters, and there's a related relationship for feet in inches, but it involves an extra constant. But if you take that ratio, what you end up with is a BMI. So it's the mass divided by your height squared. Now, BMI, the normal disclosure is there. It doesn't apply very well to individuals. It's much more of a population metric, so take it with a grain of salt. But the truth is that even though BMI is a function of these two variables, there's a very, very strong hidden time component in there. There's a time component that says, well, over time my mass changes, right? So, my weight may fluctuate due to any number of reasons, whether or not I just went to the bathroom or something like that. My height is a function of time. From the time I'm born till today, I've grown some, so that height grows. But that's not represented anywhere in here. There's no time component because these are all related. So if I wanted to take a derivative, if I wanted to see how my BMI is changing with respect to time, I have to do something that relates this thing's change in time to the variables I do have. And that's where the idea of implicit differentiation comes in. Implicit differentiation uses the chain rule to generate a derivative with respect to an additional variable there. And so as a result, we're going to use implicit differentiation, the chain rule, product rule, quotient rule, all that stuff. We're going to put all these together to develop a way of understanding the world and sort of decoupling these variables that all may relate underneath with a specific variable like time.